Hey, let's talk about how this little green filter can help you take better astrophotos in light polluted skies. Okay, so let's quickly talk about light pollution. There are three main aspects to light pollution. You've got street lights, car lights, and in-home lighting. And depending where you live, you're going to have different combinations of each of these. So that's going to make a real difference about what kind of light pollution filter you're going to want in your local area. But let's start with streetlights because they are everywhere. And they're definitely one of the most common forms of light pollution, even if you're in a not very light polluted area. So streetlights come in three major flavors. You have two sodium lights and an LED light, which tends to be rolling out a lot more these days as streetlights get upgraded. So low and high pressure sodium lights are your traditional style of streetlights. And I'm going to put up here two graphs for you to see the difference between the low and high pressure sodiums. If you're lucky enough to have low pressure sodium streetlights in your area, then it's going to be really easy for you to get a filter that just filters out mostly low sodium pressure wavelengths. They are really narrow, around the sort of 570 to 600 nanometer range. And the great thing about those is they also don't overlap with the wavelengths that you're going to get most nebulosity light from. So it's really easy to cut them out. However, I find in my area, we don't really have many low pressure sodium lights. So instead, we have a lot of high pressure sodium lights. And high pressure sodium lights, as you can see here, has a much broader spectrum of wavelengths that it gives off. There's definitely still a peak in the middle here, right around the green, yellow, and orange, which is why when you're out on the street with these high pressure sodium lights, everything has that orange tint. But this is still reasonably easy to filter out. And again, it doesn't really cross too many of the nebula light, wavelengths, which is good. Finally, you've got LED lights. Now, white LEDs, unfortunately, are really terrible. They have a very broad spectrum of light that they give off. They have a sharp peak in the blue section at around sort of 450 nanometers. Then they dip quite a bit around 500 nanometers. And then again, they sort of slowly rise up to a peak around 550 nanometers and then really slowly fall off at around 700, up to around 700 nanometers. And this makes them very difficult to filter out. But this is unfortunately the future of street lighting in most places around the world. LEDs are much cheaper, they last much longer, and they're much more energy efficient. So most councils are starting to roll these out. And in my area, I'd say it's around 40 to 50% LEDs, and the rest are high pressure sodium. So having a good quality light pollution filter will help cut out certain wavelengths. And depending where you are, you'll want a light pollution filter that cuts out the wavelengths that you're dealing with. So aside from street lights, what other lights do you have? Well, you might have car headlights. Car headlights are also moving towards LED these days, but there are also some xenon lights out there. And then you have your traditional halogen bulbs. And then finally, you have in-home lighting. A lot of in-home lighting is also moving towards LED, but it tends to be a warmer type of LED. But there's definitely still a range of traditional lights as well, like fluorescent, that are still used indoors. Hopefully this isn't too much of an issue because home sort of lighting can be shielded a bit more. Or if you're out late enough, perhaps most people have their home lights off. So in this video, I'm definitely going to be focusing more on the street light side of things, which is what I mostly have to deal with. So now that we know what light pollution is, how do we filter it? There's multiple ways, but the easiest is a filter like this. Filters can come in many different sizes. This is a 2-inch filter, and a 2-inch filter like this works really nicely with a micro four thirds or higher or larger sensor. It simply screws onto the front of the camera like this. Or you can get a filter drawer where it slots in, or you can get a filter wheel where you can have multiple filters and they rotate around. Filter wheels definitely have a great advantage because you can have multiple of them at the same time, and if you're shooting monochrome, then you're probably already using other filters and narrowband filters, so light pollution filters probably aren't needed for you. But if you're using a one-shot color camera like I am, then you are going to get fantastic results out of a light pollution filter. There are many filters out on the market these days. The one that I have here is the IDAS LPS D2 filter. It is quite a new filter. And if you live in an area with a lot of high sodium and LED lights, I would highly recommend this filter. And let's show you why. So here you can see a graph of the IDAS LPS D2 filter. And what you're seeing here in black are the spectral lines that the filter allows you to view. So you can see that between about 400 and 450, it lets 80 to 90% of the light through, which is decent. It then very quickly drops off. And this is because this is where the highest amount of light from a white LED comes in. And so it blocks that. It lets 0% or 1% of that light through, which is great. It then very quickly spikes back up until about 550 nanometers, where it sharply cuts down. And in this section here between 550 and 650 nanometers, this is where you have your low and high pressure sodium. It also cuts out a lot of the orange from the white LEDs as much as possible. And then finally, after about 650 nanometers, again, it comes back up, letting 90+% of the light through until about 700 nanometers, where it cuts down. And these three wavelength groupings that this filter allows through are the major spectral lines that nebulosity emits. So you get true color nebulosity coming through while minimizing the amount of light pollution that reaches your sensor. So what does this do? Well, the aim of this is to increase your signal to noise ratio. By decreasing the light pollution or background noise as much as possible, and only letting through the thin wavelength light from the emission nebula, then you're able to get a higher signal to noise ratio. Now, there are some drawbacks with this. Firstly, your color balance is going to be way out of whack. Secondly, you are going to get less signal. This filter, and I need to make this abundantly clear, this filter will not let you gain signal faster. At best, this filter will give you 90% of the light coming through, maybe 95% of the light coming from any one object. So you're always going to be losing a small amount of light coming from the objects. But what it does do is it drastically reduces the background noise that you're getting. And this means that while you lose a small amount of light coming from the object you're trying to image, you lose the vast majority of the unwanted light, or noise in this case, from the background. And that means that your signal is far stronger than your background, allowing you to have a higher signal to noise ratio, which will reduce the end noise that you get in your images, allowing you to increase the brightness from your images without increasing the noise. So your final result will look better, but it won't magically make your images brighter with the same amount of exposure time. So now that we've gone through what a light pollution filter is, let's jump onto the computer and go through some examples of images taken on DSLRs and on one-shot color dedicated astronomy cameras, and see how much of a difference does this make, and is it worth the money that you're going to be investing? So here we have two identical images taken on a Nikon DSLR, the D750, with a 24-70 f2.8mm lens on it. In the left one, no filter is used, and on the right one, the IDAS LPS D2 filter is used. The most obvious thing to talk about first off is the color cast. This filter will make your images green heavy. As we can see here, it is very, very obvious that more green comes in than other colors. But one thing to point out is that in this left one, we're actually yellow cast. So just down below to the left of this image is a really bright, high pressure sodium lamp, which is giving off a really yellow cast. These ones down here, if we zoom in here, these are LED lights. So they're giving off a rather white light, but just off camera down to the bottom is a high pressure sodium. The other thing that we'll want to point out here is that the right one is actually darker. And hang on. If you want to take images of the night sky, of things that are already really faint, you don't want them to be darker, do you? Well, yes. In a way you actually do. Because all the light that we see in this image is light that we don't want to actually capture in our images. Every source of light that you can see in these two images is man-made light. So ideally, the right image would be as dark as possible, because it means man-made light is cut out from the image that we want. Unfortunately, that also means we'd probably cut out the light emissions from galaxies and nebula. So we have to have a bit of a trade-off. Now, if we zoom into these images, we can see that the right one, as we mentioned, is far darker than the left one. These bushes and trees in the front here are almost black compared to being, distinguishable from each other in the left one. Another interesting factor here is if we look at the lights on these buildings. In this right one, there's a lot more shadow, and you can see the individual lines between each of these lights, whereas in the left one, you can't. And what this means is it's cutting down the amount of light that you are seeing from this very bright building off in the distance, which means less of that light is going to be interfering with the light that you're going to be getting from your target. So let's compare these two properly. If I stretch this left image and apply the same stretch to the right image, that just got even darker. Likewise, if I stretch this right image and then apply it to the left one, we see that it gets brighter. Let's bring up a histogram. Here we can see the histogram of the left image. It has a reasonable amount of color through it, and it is exposed left to middle. This is the histogram of the right image. As you can see, it is much darker because it is cutting out a huge amount of that man-made pollution, light pollution. But also the green lines and some of those reds down the bottom are a lot more distinctive than they are in the other one. So we're cutting out a lot of that blue and yellow light. So how does this work for astro images then? Well, here we have two images. Each of these are 10 30-second images integrated using the same parameters, using the same darks, and using their own lights. On the left, we have 10 30-second images and 10 flats that were integrated. And this is from my local park, where the skies are a Bortle 8 class. Again, this is taken on the ZWO ASI 294 MC Pro and -10 degrees Celsius and 120 gain. And we can see that, there's some nebulosity here. You can see some of these dark globules here, and generally it is a okay image. But on the right, we have the same 10 30-second images, everything exactly the same, 10 flats integrated, and you can see a lot more detail. Now, this isn't quite fair, because what we've done here is I've stretched them both automatically, but really, this is how the second image looks if we stretched it the same amount. So what we can see is the right image is actually a lot darker than the left image, and that's exactly what we would expect, because the light pollution filter is cutting out all that background noise. So if I zoom into this right image here and go up to the top left corner where there should be nothing but really dark space and look at the left one, we can see there is a distinct difference between the amount of background light coming and hitting the sensor. On the left one, there's so much light that it's making it a gray, whereas on the right, it is very nicely dark. But if we come over to the nebulosity here in the middle between the two, the brightness isn't that different. We can still see a lot of this detail in the middle. But what you'll notice is the contrast is just exponentially higher. The difference between the bright nebulosity and the dark background is hugely different than the bright nebulosity and the bright background on the left one. So let's do the inverse. Let's stretch this right image to an auto amount and apply that to the left image. Now, how come we don't get the same detail back in the left image? That's because it's also bringing up all of that background data. We don't have a high enough signal to noise ratio in this left image to pull the data out from the background, whereas in the right one, we can bring up the nebulosity data and the background stays dark. And this is the beauty of the light pollution filters or light suppression filters, is that they allow you to gain data on your nebulosity without losing data to the background noise. Now, this is definitely not a substitute for dark skies. You absolutely would prefer to go to dark skies and not have to use a light suppression filter if you could, but that's not always possible. Another little benefit of the light suppression filter is you can see there is a lot less star bloat in this right image. This little star here is a lot smaller than the star on the left. Again, that is because stars mostly release light at a full spectrum, so reasonably evenly across a full spectrum. Now on this right image, we are reducing the amount of light coming from those stars in comparison to the nebula. So the stars will seem a bit smaller, which means they're less likely to bloat, and you're able to actually take longer images without having that star saturate. So you might be thinking, what about color correction? Those DSLR images you were showing have a green color cast, so does that mean my images come out green? Well, the beautiful thing about this is using a program like Deep Sky Stacker or PixInsights, if you take your flats with the light suppression filter on it, then your flats are also going to be affected the same way. So when you subtract your flats, it'll actually also automatically take out the color cast. And this is how, after only stacking, and I will say here, I just did the weighted batch pre-processing script. So I did nothing fancy. These both just had the weighted batch pre-processing script with bias darks, flats, and lights integrated. That is all I have done here. Oh, no, I lie. I did also do some background removal because they were both red color cast. So aside from that, nothing else has happened here. I haven't done anything special to the light suppression filter image versus the non-light suppression filter. These have both had the exact same actions taken, and you can see that I haven't had to deal with any strange color casting on the light suppression filter, so don't worry about that. So if you try an image in a light polluted area, I would definitely recommend looking into a light suppression filter. It doesn't have to be the IDAS. In fact, IDAS itself has multiples. They have a D2, a D1, a P2, a V4, and there are many others like the Optolong L-eNhance. And really what you need to look at is what spectral lines do you need to cut out? Are you cutting out low pressure sodium, high pressure sodium, LED lights? Or is there another kind of light pollution that you are trying to remove? Once you know the wavelengths of light that you are trying to remove, you can then look at all the light suppression filters and make sure that they cut out the wavelengths of light that you need removed. And preferably not much more than that, because you want to keep as much light from the nebulas and from the galaxies as you can. So the less light that you have to cut out, well, that's good. So I'll leave you with my latest image of the Lagoon Nebula. This is 3 hours of integration taken from Bortle skies and a 1/4 moon.